In this video, we are going to discover a second type of algebraic model, and that would be exponential growth. Let's start by doing an example. A population of deer is growing by 20% every year. There are 150 deer living in a nature preserve this year. How many will be there in 4 years? We can use similar notation to when we worked on linear growth. We'll let P0 equal the starting value, and in this case that's 150. So we're starting with 150 deer, and after 1 year, P1, we are going to be adding 20% of that amount. So to take 20% of 150, we can multiply 0.2, that's the 20%, times 150. 20% of 150, 0.2 times 150 is 30, so 150 plus 30 is 180. Another way of thinking about this, or doing this computation, because we are increasing by 20%, we can take 150 and just multiply that by 1.2. The 1 keeps that original 150, and then the 0.2 is the increase. You can verify this in your calculator. 150 times 1.2 gives you the exact same answer of 180. Now in the second year, we'll now take the 180 and add 20% of that value. So we take 20% of 180, which is 36, and we're going to add that to 180 to get 216. Once again, we can get the exact same answer by multiplying by 1.2. So notice that unlike with our linear growth, with exponential growth, the amount that we're increasing by every year changes. So from the starting year to year 1, we went up by 30, and then in year 2, we went up by 36. Now, we can come up with some equations to describe what's happening, and just like in the past, we'll create a recursive equation and an explicit equation. In recursive form, what's happening is our Pn, our population after n years, is going to equal the previous year's population, that's what we call Pn minus 1, times 1.2. So in this case, every year we can multiply the previous year's population by 1.2. What does this look like as explicit form? Well, what's happening here is our starting value is 150. To get the population after 1 year, we multiply by 1.2 one time. To get the population after 2 years, we multiply by 1.2 two times. And that pattern is going to continue. Each year we multiply by an additional factor of 1.2. We can describe this in explicit form using an exponential equation. So Pn, our population, is going to equal 150 times 1.2 to the n. So we can put an exponent on that 1.2 for the number of years, and that'll indicate how many times we're multiplying by the 1.2. All right, so to answer this question, how many deer will there be in 4 years? I'm going to use my explicit equation. I'm going to take 150 times 1.2 to the 4th, and I decided to round to the nearest whole number. I got 311. So here's a quick summary of the formulas that we used. P0 is our starting value, just like in the past. And if it's growing by R%, which will convert into a decimal every time period, then after n years, our recursive formula is Pn equals 1 plus R times Pn minus 1. In my previous example, we had 20%, so as a decimal, that was 0.2. So R in the previous example was 1.2, and that's why I had that 1.2. That's my 1 plus R. All Our explicit formula will be Pn equals our starting value P0 times 1 plus r. So again, in the previous example, it was 1 plus 0.2 raised to the n power. Let's do an example. The revenue of a sporting goods store is increasing at a rate of 6% per year. If they brought in $1.4 million in 2019, predict their revenue in 2025. So the first thing I'm going to do is write my equations. In this case, the growth rate is 6%. As a decimal, we move the decimal 2 places to the left. We get 0.06. So my recursive form would be Pn equals Pn minus 1 times 1 plus 0.06, or 1.06. So what's happening in this case is every year we multiply our revenue by 1.06. In explicit form, that equation becomes Pn equals the initial amount, which was 1.4 million, and I'm going to leave that as 1.4. I'm just going to work in millions, times 1.06 to the n. So now if I want to predict their revenue in 2025, our starting year was 2019. 2025 is 6 years later. So I'm going to plug 6 in for n. 1.4 times 1.06 to the 6th. I got nearly 2 million. It was like 1.99 million. We can also work backwards. If we're given an equation, we can interpret what the various numbers are in that equation. So for example, if we have the formula Pn equals 250 times 1.095 to the n, and that's used to determine the return on an investment after n years, what specifically is this equation telling us? Well, the first number, the 250, is my P0. That's my starting value. So this is telling me that my investment is starting at $250. The thing inside the parentheses is the 1 plus r. If 1 plus r is 1.095, then r is 0.095, or moving the decimal over, 9.5%. So what this equation is telling me is that we're starting with $250. That's our initial investment. And that investment should grow by 9.5% every year. Now, in some of these problems, they may not give you the growth rate, and you're actually going to have to compute that yourself. So here's an example. We have the cost of shoes increased from $70 to $78 in 4 years due to inflation. What is the inflation rate? So first I should mention, inflation is a specific example of exponential growth. And so that's how I know this is exponential growth, because we're talking about an inflation rate. So what is the inflation rate? They're asking us to figure out what the R is, to solve for R. So I'm going to jot down my formula. Pn equals Po, 1 plus r to the n. And again, they're asking us to find r. I know the initial value is 70, that's my PO. And I know that 4 years later, so P4 is 78. 4 years later, the cost went up to 78. So I can actually go ahead and plug those numbers into the formula. My Pn will be 78. That's the future value. My starting value was 70. And n is going to be 4, because 78 was the cost 4 years later. So I've plugged numbers in for everything except for r, and now I can actually go ahead and solve for r. So if I want to get r by itself, the first thing I'm going to do is divide both sides by 70. So divide both sides by 70. Again, the goal is to get the r by itself. And I'm going to wait to put that 78 divided by 70 into my calculator, simply because I really don't want to introduce rounding errors into this problem. So I'm going to keep it as that fraction. I will eventually put that into my calculator. The next step is to get rid of that fourth power. And the opposite of raising something to the fourth power is taking the fourth root. So it's kind of like a square root, but for the fourth power. And so I'm going to take the fourth root of both sides, and that's going to allow me to get rid of that exponent. Your calculator will have a button that's going to allow you to take a fourth root. Depending on the kind of calculator you have, the button will look a little bit different. So it might be like an n square root, kind of like that. On my calculator, I have to actually go into this math menu, so I have to hit math, and then I have a button with an x square root, and that button allows me to take the fourth root. I'm happy to help any of you with your calculators before, after, or during class. So I'm going to have to put into my calculator fourth root of 78 divided by 70. And the exact order of those keystrokes will depend on exactly what kind of calculator you have. For my calculator, I type in the number 4 first, then the root button, and then I have to do parentheses 78 divided by 70. So I've written down on the screen the keystrokes I use for my calculator. Again, your calculator might be just a little bit different. When I put this into my calculator, I got 1.027, approximately. I rounded there. So if I want to solve for r, I can subtract 1. Oop, wrong way. There we go. Subtract 1. And I got r equals 0.027. I'm going to move the decimal over to write this as a percentage, and that's my final answer. My growth rate, or my inflation rate, is 2.7%. So I'm done with this problem. That's my final answer, 2.7%. But I do want to emphasize, if the problem wanted us to write an equation, we have enough information to do that now. We could write an equation, Pn equals, our starting value is 70, so I plug that in, 70. And then my 1 plus r is the 1.027. So I could just take that 1 plus r, plug that in, and then to the n. And so there's an equation that I could use if I wanted to predict the cost of these shoes in, say, 10 years or 20 years. All right, let's do another problem. This problem is actually about exponential decay. And as we'll see, the problem, the formulas, the process is going to work the exact same way. So this problem says the number of fish living in a lake has decreased from 950 in 2015 to 720 in 2018. Assuming exponential decrease will continue, we're going to first write an equation that models the number of fish in the lake n years after 2015. So just like in the previous problem, we don't know what the r is. We don't know what the decay rate is. And so we're going to have to go ahead and solve for that before we can get our equation. So a lot like in the previous problem. I do know that my starting value, the P0, is 915. And that, or I said that wrong, 950. And that corresponds with the year 2015. In 2018, which is 3 years later, my population is 720. So that means P3 equals 720. I'm going to plug these numbers into that exponential equation. So the 720 is my Pn, 950 is P0, so 720 equals 950, 1 plus r to the 3, because 3 years have gone by. I'm going to solve this equation for r the exact same way I did in the previous problem. So if I want to get the r by itself, the first thing I have to do is divide both sides by 950. We're dividing because the 950 is being multiplied by the 1 plus r, and we always want to do the opposite when we're solving. I'm going to wait to put that into my calculator just because I don't want to get rounding errors in the problem. So I'm going to leave it as 720 over 950 equals 1 plus r to the third. I will use my calculator eventually. All right, so now I need to get rid of that exponent, the third power. The opposite of the third power is taking the cube root of both sides. And this is where I will have to use my calculator. Your calculator might actually have a cube root button on it. If not, you have either that n root or x root button. And so I'm going to take the cube root of the fraction 720 divided by 950. I put that into my calculator, and I got 0.9117. That's going to equal 1 plus r. Now, we could solve this for r, and we will have to do that eventually, so I'll just do that right now. Notice if we subtract 1 from both sides, we get a negative number. And that's okay. We're getting a negative number because this is actually a decay problem. The number of fish is going down. So I got negative 0.0883. If I move the decimal over, I get 8.83%. And again, that negative is telling me that the number of fish is going down. So number of fish is going down by just under 9% every year. All right, back to the problem. What are they asking me for? Part A is asking me to write the equation. And so my equation is Pn equals initial value, which is 950. And then the 1 plus r, I have it circled in blue, but the 1 plus r is actually that 0.9117. So I'm just going to go ahead and plug that in. 0.9117 is my 1 plus r, so 0.9117 to the n. So there's part A, there's my exponential equation. Part B is asking me for the decay rate, and I did already compute that. That's the r value. So the percentage that it's going down by is 8.83%. Finally, the last thing it wants is us to predict the number of fish living in the lake in 2035. Our starting year was 2015. 2035 is 20 years later. So to answer this, I'm just going to go ahead and plug 20 in for n. So I will use my calculator again. 950 times 0.9117 to the 20th power. And I rounded to the nearest whole number and got approximately 120 fish.